on chapter 2, chapter 2, and then I will start state space. Yeah, towards the end of that week 10, I will start state space. Very easy on the chapter 3, and also chapter 4. The revision on the matrices, is that will not take so much time. Okay, and then we will do our test 2 in week 11. Now week 11, as you can see from the calendar, I think I miscount the week. All right, this week would be, okay, hold on, my friends keep coming in. Actually, if you are using the UiTM email, I don't have to allow you. You can just join in through the links. GM link. All right, now here week 9, this week. Week 10 is here. The initial plan was to do our test 2 here, right? The second, but that is still week 10, not yet week 11. Week 11 is after the special break here. We have a special break here, the festive week. Okay, in this the 27th of December, that week you have a leave, a special leave, and then we'll continue back on at the early of next year, where from the discussion with your class rep, the date that we would like to suggest, for doing our test 2, is on 6th of this January, 6th of January 22. Okay, so I want to ask you whether you are available at 5 p.m. to do our test 2 on this date, 6th of January. Right, if you have any classes, any of you, if you have any classes, please do tell me, because I don't want to use some other lecturer's time to do your test. It is wrong. They will blame me. It is wrong. If you don't have anything and you think that is good to make your test, that you are available to do your test, then we can agree on the 6th January. All right. Okay, I need the final answer on Thursday, this coming Thursday. You have your class, group G, on Thursday. Okay, I need to know whether it's okay with you to do your test on 6th of January. Okay, all right. Let's move on. That's one thing about test 2. I think that most of you are here now. Let's start with the lead compensator. Okay, as what you have learned before in your root locus. Guys, are you ready? Can I start?
Yes.
Okay, thank you. All right. For lead is like the root locus that you have covered before. Come on. Iskandar is here or not? Is Iskandar here today? Do anybody knows about Iskandar? Is he okay now? Right. Okay. All right. Like what you have learned before for the root locus. From the root locus, transient response improvement needs the lead compensator. Okay. So here the same concept. You need the lead compensator, and for this topic, you are looking at the course outcomes second and third. Okay, the second is the ability of you to analyze the performance of your system using the method, which is the frequency response method, and thirdly, the third outcome is about the compensator design. Okay, same like the leg, all right, leg design. Okay, yeah, this is from your the slides, PDF slides that I've already shared with you before. Okay, if you look at the lines here, the lead compensator is used to increase the bandwidth of the system, yeah, in order for you to improve the transient response of the system. Okay, bandwidth is the keyword there. Yeah, keyword there. Yeah, let's look at. Okay, so you can see that the reshaping of the high frequency response of the magnitude to get the desired phase margin. Okay, so yes, several lines there. Okay, now you come back here and read back. Okay, but now I'm going to show you the picture. Okay, this picture. All right. um I think I also have that here. Yes, all right. Now let's look at here. Same like on the, like with the text. This is the textbook. Okay, from the textbook, number 9. Okay, so I do have the same thing here. Okay, so I will open this one instead. Okay, now if you read through the lines, yeah, is to increase the bandwidth by increasing the gain crossover frequency. What is this? Omega GCO. Where do you get omega GCO? Omega GCO, gain crossover frequency, means it is when your magnitude plot, yeah, magnitude response crosses 0, gain crossover, that 0 dB. Yeah, okay, so that is where you have your omega down here. Yeah, the omega. Yeah, omega. All right, so your omega is there. Okay, so in other words, that is where, yeah, that is where you start reading your phase margin, right, from the phase plot. Okay, so that is omega GCO. So here, increasing bandwidth, at the same time you are increasing the gain crossover frequency, yeah, by using the lead compensator. Now let's look at this plot. Okay, let me explain about this plot. Now, this bold black line, yeah, is the uncompensated system magnitude plot. Okay, now this one, can you see the blue line there? Yeah, okay, so this one is the compensator line. Yeah, compensator's magnitude response. Yeah, okay, so this one. Now, remember lag, your lag compensator. Okay, you draw it this way, isn't it? Okay, you draw it starting from PC. It goes down with a slope of minus 20 dB per decade and then straight again. Yeah, so you can see that it is opposite like what you will have with the lead compensator. Yeah, you're going to draw this, yeah, based on the calculated PC and ZC from the steps. Okay, so lag is going downwards, lead you can see is going upward, and because of that, you know, GCG, the lead compensated transfer function. Yeah, because of that, GC times G, the original G, which is coming from this one. Yeah, GCG multiply. So in the semi-log graph, it becomes plus, right? Okay, so here the both solid black line, yeah, plus with that GC becomes that line. Yeah, I hope that you can see my cursor. That is the lead compensated magnitude plot. Okay, all right. Okay, so you can see that what happened to this new line is that the omega GCO has been increased. Why? Look at the A and the C. Yeah, So A is lower, smaller value than the C, because you're talking about the frequency here. Lower frequency, higher frequency. Okay? Doing that, in other words, at the same time, you're also increasing the bandwidth frequency. Okay, I'm going to explain to you about this bandwidth frequency, how to read the bandwidth frequency from the board plots. Okay, all right. Now, having that, yeah, this is becoming the new phase margin. Yeah, okay. Now, okay, we skip on that first because that is the step. I want to explain about, okay, why bandwidth? What it has, why it has to do with this the transient response parameters, the TP, the TS, the TR. Okay, so here we focus on these two, TP and the TS, yeah, as they can be related with the omega bandwidth. Okay, right, hold on. Okay, I cannot see my laptop. Okay, yeah. Can you see the slide? This slide, yeah, the equation down here. Can you see it?
Can, yes.
Can you see?
Can.
It's a bit lower, yeah. At this on this page, yeah. Omega bandwidth is related with 4 over Ts. Okay, hold on. Iskandar is here. Iskandar. Okay. Thank you for joining, Iskandar. Are you good today? Are you feeling well now? I hope that you are fine. Yeah, Iskandar. Yeah, okay, all right. Let's continue. Okay, omega bandwidth. Okay, look at the equation. This is with TS and this is with TP. Now, what do you think about the relationship? Is it direct proportional to TS and TP, or how? The omega bandwidth is inversely proportional, isn't it? Yeah. Okay, when it is inversely proportional, you can see that when you increase the bandwidth frequency, you will have better performance of the system in terms of the response time, right? Yeah, the peak time shorter, TS also shorter. Okay, now let's look at the bandwidth, yeah, frequency. All right, so here is what I meant just now. You can increase the bandwidth frequency, yeah, using the lead compensator. Now, how to read the bandwidth? That's the question now, right? Okay, I ask you a question, yeah, before I start. Bandwidth. What do you understand by bandwidth so far? Where do you have this term bandwidth used in your subject? Can you tell me?
Communication.
Hmm?
Communication.
Communication. So what do you understand by bandwidth? Why is it so important?
Showing the
The
strength of,
strength of
strength of, no
the
idea.
signal.
Yeah, signal.
The strength of the signal that you want to transmit, right?
Yes.
Okay, so that is important, isn't it? You must make sure that, yeah, your signal is within the bandwidth so that you can transmit the signal, you can have the signal, yeah, not transmitted, yeah, transmitted as much as possible. Okay, so the same goes here, yeah, in control. You're talking about bandwidth. In other words, you're talking about the signal that we want from the system. Okay, it need to be um, in the amount that we can use. All right. Okay, so if it is not within the bandwidth, then meaning that the signal will be distorted. You will lose some of the data. Okay, and that bandwidth you can get read from the graph. Okay, so how is it related to the TP and TS? Okay, it is related by the equation just now. Yeah, and then if you have, you can read, if you know your bandwidth. Yeah, and then if you can increase the bandwidth, that is better. You can push some more about your system to make it faster. So increasing bandwidth is good, right? And that can be done by doing the lead compensator. Okay, related with the TP and TS, increased bandwidth would be able to shorten your TS and TP by this relationship. Okay, got it? Yeah. All right, now I will explain more about the bandwidth by using this page. Right, this is from the textbook. Okay, now I think that you are, yeah, when you talk about bandwidth, you also know about minus 3 dB. Okay, that is in dB. Yeah, the minus 3 is where you can read your bandwidth frequency. Okay, if I open my graph, okay, let me open my graph here. Okay, let me show you the concept graph first. Okay, before I show the real graph. Okay, when you talk about minus 3 dB, to look for your bandwidth frequency from both graph. Okay, now can you see my cursor? Can you see my cursor? Yeah. Okay. Now you're looking at minus 3. dB is here, right? dB. Yeah, the magnitude. Minus 3 dB means that you're looking at where this magnitude line, yeah, at minus 3 dB, the frequency where you have that minus 3 dB of that line. Okay, that is where you can get your omega bandwidth. All right, now you have a problem here. Minus 3 dB is for closed loop bandwidth frequency. Okay, but the plots that you have drawn, yeah, right from the beginning, yeah, of our chapter 2 is from the open loop transfer function equation. So you call it as open loop magnitude plots and phase plots. Open loop, yeah, frequency response. So you don't have closed loop closed loop frequency response. Yeah, to read this the omega bandwidth at minus 3. Okay, that's the problem. But okay, in the textbook, it is stated here, look down here, the closed loop magnitude response minus 3 dB, yeah, the frequency at which you get this minus 3 dB of the magnitude response is equivalent to, yeah, okay, let's continue on the next page, to the frequency at which, yeah, you can read, yeah, minus 6 to minus 7.5 dB from your open loop magnitude response. Do you understand what I mean? Okay, so minus 3 dB is the magnitude response value that you use to read the omega bandwidth frequency. Okay, but the graph that you have is from the open loop transfer function. So can you use minus 3 dB to read your frequency? Cannot. Okay, instead, yeah, it is proven here that you can read the omega bandwidth, yeah, not at where you get minus 3 dB, but in this range, minus 6 to minus 7.5 dB. Okay, so in other words, if I open up my this one, yeah, so not minus 3 that you are looking for, you are looking for minus 6 to minus 7.5 dB. Now let's take a minus 7, okay, for you to memorize, easy to memorize. Yeah, minus 7 typical value, minus 7, and then you find your minus 7 from the magnitude response, and then you read the omega as the omega bandwidth. Okay, because this is open loop magnitude response. Okay, so this is the open loop phase plot, right? Not the closed loop frequency response. Okay, so that is what it means by this pitch. Okay, the lines here. Okay, so you can read, yeah, between minus 6 to minus 7.5 dB. Now jot that down in your notes. Okay, I start back from the speech. Okay, talking about minus 3 dB for closed loop magnitude response. Yeah, but since you don't have the closed loop magnitude response, but you have, yeah, the open loop magnitude response. Why? Because you are using the open loop transfer function, yeah, KGH, to plot your magnitude and the phase plots. Okay, but not to worry. Yeah, instead of minus 3, you're talking about minus 6 to minus 7.5 dB now to get the omega bandwidth. Yeah, so that is the parameter that you can get. Yeah, you can read from your graph later. Yeah, you want to check, okay, whether is it true that my bandwidth increase or not? Is it complying the requirement about the time or not? Okay, you're going to do that, yeah, in the steps. Okay. Now, is there any question until there? Yeah. Okay, now when you design a compensator, lead compensator, yeah, you have to draw the red line afterwards, yeah, at the end. Okay, when you do that, yeah, it's obvious, right? When you lift up, yeah, the upper part of the magnitude response, yeah, you will increase the omega GCO as well as the omega bandwidth also will be increased. Okay, because this part, the upper frequency part of that magnitude response, will shift up. Yeah. Okay, so that is the concept of applying lead compensator to your system, yeah, to improve the transfer response. Okay. Now it is still early, yeah, 12:30. Okay, let's move on directly to the steps. Okay, all right. Okay, steps I will be using, okay, I will close this one. I'll be using from the normalize, yeah. The steps are here. Yes, here you are. The design procedure, yeah. Okay, so 1 until there, 10. Okay, you're going to um, use all the steps, okay, to answer this question. Okay, this question. Right, remember the question? Okay, look again, yeah. Let's look at the question now. Okay, any question? Yeah, you stop me and ask me. Okay, if anywhere that you need me to repeat, please tell me. Yeah. Okay, let's look at the question. Okay, you are given with this Yeah, same system in figure 11.2. Remember 11.2? The plot diagram, right? Yeah, where you have your kgh equals to 100 times k over s 3 plus 36 over s plus 100. Yeah, so that is kgh of your system. Okay, open loop transfer function to be used to plot your board. Yeah, okay. Now, using the same system, yeah, you are required to design the leak compensator to yield 20% of overshoot. That is one requirement. Okay, mark that. Okay, let me highlight. Yeah. Okay, so you have all right, 20% overshoot. That's one. Secondly, KV equals to 40. That is the next one. And the last one is the peak time. Yeah, TP equals to 0.1 second is the requirement here. Okay, right? So that is the equation that you have used to plot your graph. Okay, so remember three things here. Okay, right, lead compensator. Yeah, use that to achieve, to solve the requirement. All right, now step number one. Ready? Am I going too fast? Are you ready?
Yes.
Yes? Okay, shall we? All right, let's start. Take out your graph. Okay, thank you. Take out your graph. Yeah, okay. You need your notes here to write down the answer for each step. All right, number one. It asks you to calculate the closed loop bandwidth for the required. Okay, hold on. Okay, calculate the closed loop bandwidth for the required peak time. You don't have, you are not given with the settling time, but you're given with the peak time, right? TP of 0.1 second. Now, I need you to calculate this later. Yeah, when we go to step number 10. Yeah, when we are at 10, later on, okay, do this number one. All right, now let's look at number two. Okay, so here you need to set the K of the uncompensated system so that it satisfy the steady state error requirement. Now, what is about that given in the question? It is given by the KV, right? Okay, in the question you're given with the KV, the second requirement, 40. Right now, what is KV? Yeah, in its equation, with the open loop transfer function. Yeah, so limit s to 0, then you have k. That is the original equation, isn't it? 36, and then you have s plus, s plus 100. Okay, all right. Okay, yeah. Okay, you have that equation. Okay, now look here. You have your k. Yeah, you have k. So since kv is given to you, that you can use to calculate your k. Okay, calculate now. What do you get? That is the equation that you know, right? Limit of your kgh there, you put back and you calculate the k. Yeah, so remember number two, it asks you to find the k. Why do you need the k? Because you want to plot. You always need a k to plot. Yeah, okay, 1440.
1440.
Yes, Hilton. Yes, Alia. Isn't it that is the value of k that I asked you to plot your board plot with?
Yes.
Yeah. Okay. The reason is here. Okay. The reason is here. You get k equals to 1440 there. 1440 is actually is the value of k if you use your kv there given in the question. Okay, using that k you solve number 3, you plot number 3. Plot the board plot as in step number 3. So 2 done, 3 done. Any question? Okay, if you look at gain adjustment, gain adjustment. If you can recall, how do you plot your board plot? You need a K, right? Remember, gain adjustment, you have to select a K. Okay, so from our exercise, we select a K so that the magnitude response starts at 0 dB, right? Okay, so it means that you need a K to plot, right? Lag compensation. From lag also, okay, you have it plotted, but it started from the K that you select, and then based on the improvement on the error as required in the question, you apply another K, which is the KSSE. Okay, all right. So here, whenever that you have this kind of design question, remember, bear in mind, what is the value of K that I need to use to start your graph? Okay, you need to have a K. So here, find any information that can help you to calculate the K. So for this exercise, you're given with the KV. You can get the K from there and start plotting. Okay. All right. Now, next, let's look at number 4. Tell me if you need me to repeat. Anywhere. Okay. Ready? Number 4. Find the phase margin to meet the damping ratio or percentage overshoot required in the question. Now, you have 20% overshoot, right? In the question. Look back at the question. Okay, so here you have 20% overshoot. Yes, there is a requirement. So it means that you need to find the phase margin. Means, okay, from your 20% overshoot, okay, overshoot, get the zeta. Right? Because you need to use the zeta to calculate your desired phase margin. Okay, so what do you want to use? FD, phase margin desired. FD in short. Boleh? Okay. Alright, so which equation to use? Okay, we have done this before. During your gain adjustment, you have been introduced with the equation, to calculate the phase margin. Okay, let me open that for you. Put gain adjustment. Right, calculate for me now what is your FD, using, okay, where is the formula? This one. Okay, you have used this before, during your gain adjustment, okay, and also the zeta also you use it. The phase margin you use it in the okay, in lag, right? Okay, so here zeta, calculate first for me and then tell me what is the phase desired, phase margin desired, from this equation. Do this now. Okay, tell me what you get. For zeta. Yeah, I think I have some answer there. Okay, thank you very much. We stand. Yes, yeah. Zeta is equals to 0.456. Yes, that's correct. Okay, next, phase margin. Yeah, calculate now. That's quite a long equation for you to calculate, right? The zeta with the, yeah, quite high order there. Third, yeah, twice inside the equation. So be careful. Okay, so here Siti Nabila has calculated 52. Can I have second answer? Siti Nabila, can you check back? Yeah, it is slightly different.
48.5.
Yes, it should be
Okay.
48.1 something.
Okay.
Yeah, okay. Right, so 48.1, yeah, is should be the answer. Yeah, slightly different in decimal is fine. Yeah, not so much. Okay. Okay, I put there, yeah, here. Okay, so here is equals to 48.1. Yeah, based on the equation, right? Okay, now find the phase margin to meet the percentage overshoot as required. Yes, we have got it. Yeah, 48.1 is the answer. Then evaluate the additional phase contribution required from the compensator. Okay, what is this? Okay, phase contribution is actually the fee max. Okay, let me write it down for you. It is here, fee max, we call it as fee max. Okay, I called it as, I name it as fee max, yeah? Fee max, right, equals to the fee of D, the desired, minus, okay, fee of what you get from the graph. Fee, what is fee? Fee is the phase margin, okay, plus the correction factor. Okay, now here you get the fee D there. Okay, and what about the fee uncompensated from the graph? Fee UNC, okay, this one, UNC, I don't want to write so long, yeah. Uncompensated, I cut it short, UNC. Shall we? Yeah, so this fee uncompensated, you need to read from your graph. All right, now let's look at your graph. Okay, this is your graph. You have to read what is the current phase margin, yeah, from your graph. Okay, let's look at your graph. Yeah, your graph should start the magnitude plot at 52, right? 52, and then you plot using the same slopes that you have you have used before, yeah, for another K. All right. So here with the new starting point 52, you plot, and here you are. The omega GCO is there. Omega GCO. Yeah, the magnitude where you have it crossing the 0 dB, and then you can read your omega. Yeah, omega GCO, or in other words, you can also put as omega PM. It doesn't matter. Yeah, it's the same thing. Okay, right. So here, when it crosses 0, that is where you start reading the phase plot for the phase margin. Okay, so that goes back to the definition of phase margin and gain margin. Yeah. Now, can you look at your own graph and tell me what is your current phase margin? Okay, my case here, yeah, where it crosses 0 dB, yeah, I start reading the phase plot. Yeah, so phase plot here, I have about four boxes there. 4 times 4.5, because my scale is one box equals to 4.5 degree. Okay, so that gives me 18. Okay, tell me yours.
Same.
Hmm?
Same.
Sultan, you have the same 4
Yes.
boxes? Okay,
Yes.
label, yeah, thank you. Label your omega, please, down there. Yeah, at the frequency line, yeah, you mark your omega PM there. That is also omega GCO, yeah. Okay. Do I have any other answer than 18? 13.5. 13.5 means, Lukman, how many boxes that you have? Where is my calculator? Okay, I use my handphone then. Is it 3 boxes that you have? 3 times 4.5. Yes. Yeah, 3 boxes. Okay. All right. Take your answer. Take your answer. Okay. Anybody else? Yeah. Do you have any other answer? Okay. Why Lukman's answer is very a bit far from what I have, or Shilton. Yeah, Shilton also got 18, right? Yeah. Because one box, yeah, has a difference of 4.5, right? 4.5 degree. Okay, 4.5 degree. Okay, so that is why 18 and 13.5. Maybe some of you got 5 boxes, and that gives you 12, no, sorry, 22, 22.5. Okay, so take your own answer. Yeah, and let's continue with the steps. Okay, 18. All right, let's take 18, yeah, as what I've got here. Yeah, so here, your answer for Fimax, calculate it now. Yeah. My phase margin from the uncompensated magnitude uh, and the phase plots, yeah, gives me 18 degree. Okay, so you have 48.1, 18 degree, put them inside here. Okay, now correction factor here, remember from lag, yeah, we use 5 to correction factor. Okay, where should I put it? Here. Okay, correction factor is from 5 to 12 degree, right? 5 to 12. Okay, but in the question it's not required here with any value, so it means that you can just apply 10. The typical value is easy to remember, yeah, plus 10. Okay, so get that and give me your answer for Femex.
40.14.
Yeah, 40.14. Okay, 40.1. Okay, all right, so 4 finish. Okay, we get Femex. Okay, got it? If yes, shall we go to step number 5? Yeah. Okay, if you think that I'm too fast, you tell me, okay? Number 5, you have to calculate beta. Beta using the phi max that you have calculated in step number 4. Okay, what is the equation that you need to use? All right, now, in the previous page, yeah, okay, let me reduce the size. Okay, you have this page. Okay, you have this page. Don't worry. Yeah, all these equations are also written in the slide. Okay, so this is the slide. Right now, let me use this slide instead. Yeah, so that you don't have to be worried. Yeah, GC. Yeah, look at the formula. GC. Here, the G lead there is also the GC. Okay, that one, if you look carefully, it is the same equation that we used before. Yeah, GC equals to KC S plus ZC divided by S plus BC. Same. Yeah. So here ZC equals to 1 over T. Okay. So ZC equals to 1 over T is written here. PC equals to that. It's written there. Okay. And the KC equals to 1 over beta. See? 1 over beta. Yeah. So KC equals to PC over ZC equals to 1 over beta over 1 over beta T divided by 1 over T. Yeah, so you have 1 over beta. Right, so that is about GC. Okay, you're looking at beta, right? Okay, where is my beta? Okay, right. Okay, here. Yeah, on page 7. Yeah, so beta is okay here. Right here is your beta. Okay, it actually starts from here. Yeah, like also in the textbook, it also starts from here, and you rearrange it to get beta as what, as the left side, because that is what you want to calculate based on the phi max. Okay, phi max, step number 4, we have got it. Okay, you're going to put the phi max here. Yeah, the example that I have here, 40.1. Yeah, from my graph. Yeah, the phi max, you calculate it, and I get 40.1. I put it here to get my beta. Okay, all right, so calculate this now. Use this formula.
Zero point 0.22.
Yeah, okay, 0.22. Yeah, okay. Let's write it down. Okay, number 5. Okay, 5. You have got your beta based on that equation. 1 minus sine phi divided by 1 plus sine phi. Yeah, phi max, equals to 0.22, yeah, from your friend's answer, or 0.216. Okay, let's use 3 decimal point. Okay, okay, 0.216. Done. Finish. Okay, Nukman, you will get another answer. Yeah, don't have to worry. Yeah, your beta may is slightly, I'm not sure, bigger or smaller. Maybe bigger, is it, Nukman? Can you share your beta? Because you got your fee uncompensated 13.5, right? Smaller. Okay. Okay, you get smaller value of beta. Yeah, stick to that. Don't worry because the step is fine. The same steps. Okay, next. Next, okay, right. Number 6. Tell me if you need to need me to repeat. Okay. Number 6, you have to calculate for the magnitude at the peak of the phase curve. What is this? What is this? Yeah. Okay. Let me tell you what is this. Yeah. This is the M. Yeah. M max calculation. Yeah. So this one. Yeah. You have to use this formula. Using the beta, you have to calculate this one. This one. Okay, can you see the equation down here? This one. Yeah. Okay, this one. Yeah, I also can write this as M max. Yeah, because I don't want to write so long like this. Yeah. So I want to use simple terms. Yeah, M max. Okay, so to calculate M max is to get to use this one 1 over cert beta. Okay, calculate now.
2.15.
2.15. Yes. Okay. Next. Oh, on the graph. Yeah. On the graph. Okay. This one on the graph. Yeah. You have to use 20 log. Yeah. Because this is magnitude. Yes. But it is not yet a value that you can refer. Yeah. To your on your graph. Yeah. 20 log M max. Okay. Then only you get it in dB. Okay, what's the value here? All right. Yeah. Okay, get it. 20 log. Daniel Fitri, yes. 2.15.
6.66.
Yes, apa? Shelton?
6.66.
Yes, yes, that's right. Okay, you have 6.6 something dB, right? Okay, let me write down the value. Yeah. Okay. I write mine. Yeah. You know your values already. Okay, and they are correct. Yeah. Okay. Use yours. Okay. This is just for reference. Yeah, for your friends. Okay. 2.149 and 20 log of M max is 6 point. Okay, I take 3 decimal point 646 dB. See, dB. Okay, you can write or always write it. Yeah, it's in dB. Because why? This is to avoid you, yeah, from forgetting to 20 log, not to have this 2.149 only. Yeah, but you are looking at the graph afterwards for this value, so you have to use the 20 log of that M max. Okay, and that is to finish with step number 6. Any questions so far? Nope. Okay, thank you. Okay, shall we? Okay, let's move on to step number 7. Okay. All right, number 7 says what? Okay, you have to find the new phase margin frequency. The new phase margin frequency by finding where the magnitude curve just now, the number 6, yeah, is the negative. Where okay, you have to find the new phase margin frequency. Okay, from the magnitude curve that you have plotted, okay, at where you can get the negative of the value from here. Okay, new phase margin frequency, you have to find the omega. Okay, I name it as omega max. Okay, number 7, omega max. This is the frequency where you can find the negative of this, which is negative 6.646 dB, yeah, on the magnitude plot that you have plotted. Okay, all right. So omega max is found at where? Yeah, for this negative 6.646. All right, now let's look at the graph. Okay, you're looking at minus 6.646. Okay, look at my graph. Yeah, so minus 6 of the magnitude plot. Okay, be careful not to read the phase plot. Yeah, read the magnitude plot. Yeah, so minus 6.6 is about minus 7, right? So it's about here. It's about here. And then you read down for the frequency. Yeah, and label it as omega max. Okay, I repeat. Okay, from the previous step where you get your 20 log m max, okay, take the negative of that, which is negative 6.6 dB. Okay, look at it, yeah, from the magnitude plot. Okay, find where you get that negative 6.6 and then get the frequency. Okay, you label it down here, yeah, downwards as omega max. Now I have it here with my sketch here for that. Okay, not so clear, isn't it? But I hope that you can view, yeah, what I'm doing here. Okay, this is the GSSE. Why GSSE? Because of the KV. I just name it as GSSE. Okay, right. So then I'm trying to locate where is my minus 6.6. It's about there of the magnitude of plot, and then I'm looking for the omega, to get that value. Okay, so that one I mark it as omega max. Look at your graph, tell me what do you get for omega max now.
54.
54, okay, 54. Okay, other than that, 58, Uman, okay. Other than that, we stand 52, yes. Right, you know what you're doing, right? Okay, that's correct. Yeah, mine is 56, about that value. Doesn't matter if with 52, 58, they're all okay. Fine, correct. Because you're looking at your graph. Yeah, so Daniel Fitri, okay, same with me, 56, yes. Yeah, so omega max 56, yeah, radian per second, yeah. Okay, from the graph, yeah, this is what you read from the graph. Okay, omega max equals to 50 radian per second, yeah, found for negative, I put back, yeah, 6.646 dB. Yeah, so omega max is found at 56 radian per second for the negative 6.646 dB from the graph. Right? Okay, so that is step number 7 done. Okay, now you have got your beta, you have got your omega max. Next is to solve for the 1 over t. Yeah, 1 over t. What's the formula? Here you are, you have the formula here. Okay, where is it? Yes, this one. This one. Okay. All right. So how to get 1 over t? So you just rearrange, right? Okay, 1 over t equals to omega max times the b, the beta. Yeah, omega max times the beta. Yeah, to get the 1 over t. Why is this that you need to have the 1 over t? Because 1 over t is your ZC. Can you see that? Yeah. Okay. And then that 1 over t, or the ZC, you divide by beta, you'll get your PC. Okay. Right. So that is step number 8. Is to get the ZC, the PC, based on the 1 over t that you can calculate from omega max. Okay. So I write it down here. Okay. And you can continue. Okay. To get from omega max. Yeah. Okay. 1 over t. Yeah. 1 over t equals to omega max sub beta, and that is your ZC. Okay. Then get your PC. Then get your KC. Okay. All right. Together. Yeah. PC, ZC, KC. You will get your GC. Okay. Write down your GC. Yeah. Putting in the value of KC, ZC, and the PC. Yeah. Inside the equation, you will get your GC transfer function. Okay. I write back here. Okay. There you are. Finish with GC. Yeah. Okay, tell me, what do you get for PC and ZC? Okay, calculate now. Got it? Okay, can you tell me what you get for your PC and ZC? Okay, thank you, Numan. ZC 24. Yes, about the value. Yes, ZC, and then PC is 138. Yes. Yeah, okay. Right. So you can see PC is greater, yeah, than the ZC. So means that you have lead. Yeah, PC greater value than ZC. Here you have a lead. Okay, you can recall the S-plane plot, yeah, where you have your PC and ZC plotted for lead compensator last time during the root locus. Okay, all right. Okay, now is azan. Okay, write down for me GCG. Yeah, write down. Okay, let's have a break, 5 minutes. Yeah, we'll continue 1:15. Okay. We are at step number 10. Yeah, 9, 10. Why? What is this? This is the KC. KC, how to get the KC, which is the PC over ZC or 1 over beta. Okay, now just to make sure that you are writing this correctly, GCG, yeah, is the KC with that one, yeah, the whole thing here, yeah, you put it there, okay. Okay, G, what is G? G is the 100 K over S36 S100, right? K, don't forget to put 1440 from step number 2 just now. Got it? Yeah. Okay, so you have the KC the K1440, and then the 100 initially you have it in the original equation, right? Yeah, 100K, isn't it? So 100, don't forget. Okay, so you have them all together. The constant values you can multiply. Okay, right? So that is your GCG done. Okay, right. What's next? Okay, here number 10. Check the bandwidth to make sure, yeah, that the speed requirement is met. Speed requirement is about TP, right? From the question, TP. You see the question here. TP is 0.1. Yeah, seconds. So the 10 is asking about, okay, now please check. Yeah, is it that the design has met the speed requirement or not? Okay, so how to do this? Yeah, is by taking back number one. Number one, just now we skip, right? Okay, you have to take it back and then go back here. Yeah, do it together with number 10. Okay, you have to calculate first the closed loop bandwidth that is required to meet the peak time in the question. Okay, so 0.1, use the, okay, not this one, close that. Okay, where is the equation? Here. Yeah, you have the equation on this page. Yes, okay. So take this equation, okay, calculate for me the omega bandwidth desired now. Okay, let's put a name, omega BWDES, yeah, something like that. Yeah, omega BW desired. Okay, calculate for me what is the value that you get. From the question is 0.1 TP. Okay, so it means that this is the desired frequency response. Later, you are going to compare with what you have got in the graph. Yeah, okay, calculate for me now for this one first. It's quite a long equation, yeah, to use. Yeah, so careful. So what again? Yeah, omega bandwidth from this equation. Yeah, the required bandwidth frequency, yeah, is equals to oh, wow, okay, yes, 46 point. Okay, hold on, let me check the chat box, yeah, from Daniel. Okay, 46.6. Yes, you're right. That's the answer. 46,594. Okay? Yes, that's right. Okay, so everybody else, yeah, you can refer to the chat box. That's the correct answer. Yeah. Okay, now going back to the steps here. Right, okay, you have calculated number one, yeah, for the closed loop bandwidth required, yeah, for the 0.1 a second TP. And then, okay, so here, okay, you have to check the bandwidth, the bandwidth of the compensated system. Okay, that is number 10. This is quite difficult, yeah. Okay, what you need to do is that, okay, am I too fast? Okay, let me tell you what is about number 10 first. Okay, now first of all, to answer number 10, okay, you have to plot the red color line. Okay, the red color line you have to plot. How to plot that is by plotting the GC first. Now you get your ZC, you get your PC, right? ZC, PC, you've got it already. Okay, so what's next is to use the values of your PC and ZC to plot this GC. Okay, after you plot your GC, you sum the GC that is 20 log on the graph. Okay, so this line, magnitude response line of GC, you plus with the original line, the GSSE, where you use the K equals to 1440 in step 2. Yeah, sum this together, this and that together, you will get the red color line. Okay, now from the red color line, this is what you call as the lead compensated magnitude curve or magnitude response. Okay, now remember my explanation about bandwidth frequency? From normalized textbook says that since this is open loop magnitude response curve, yeah, you have to look at not minus 3 but between minus 6 to minus 7.5 dB. So here minus 7, I try and get the minus 7 there that hit the new line GCG and read the omega bandwidth for the omega bandwidth from design that you have got. Here I have got 100 radian per second. Okay, and then you can start comparing between the desired just now, the 46 point, what's the value that your friend got just now? 46.594 with this 100 radian per second. Which one is greater? If my design has greater value of bandwidth, isn't it that is better? Greater bandwidth is what you need, right? So the design is good enough. The design met the requirement of the 0.1 second of TP. Because having greater bandwidth frequency, you will get shorter than 0.1 second TP. Okay, that is to answer 10. But you haven't got your graph yet. Okay, now, okay, today, since we still have time, 1:30 now, I want you to plot for me, yeah, this line first, GC line. How to plot this? Yeah, I will tell you. Ready? Okay, my ZC is 26. Yeah, 26.03. So 26. Okay, I mark where I have my ZC first. ZC and PC together. Okay, I mark the ZC and PC on the graph, on the scale of this frequency line. Okay, label there, yeah, where you have calculated your ZCPC just now. You label your ZC and PC location. Okay, so in my case, I have PC equals to 120.49. Okay, so that is where I have my PC, put it there, my ZC, put it there. Yeah, PC is 26. Okay, like your friend Lukman here, ZC equals to 24. Now look for 24. Yeah, Lukman. Okay, 24, you look for 24 and you mark your ZC. Okay, PC is 138. 138 is next to mine. Yeah, next to my PC. Okay, 138 is somewhere there, probably. Yeah, okay, so label it and then next. Okay, I take my example. Okay, ZC is at 26 and the PC is at 120.49. Okay, all right, now how to do this? Okay, look carefully. Starting from ZC, starting from ZC, then only you can plot the line with this slope. What is that slope? Positive 20 dB per decade. Remember lag last time? Lag you use negative 20 dB per decade. Right? So here for lead, you have to plot for positive 20 dB per decade. Okay, so before ZC, it's all the way 0 on the 0 dB line. Starting from where you get your ZC, you start measuring, yeah, for that positive 20 dB per decade. Now, to get positive 20 dB per decade means that, okay, if my ZC is at 26, okay, in one decade, I'm looking at 260. You understand what I mean? One decade from 26 is 260 here. Okay, I mark the value there, and at that frequency in one decade, I should have positive 20 up from 0 dB, exactly 2 centimeter. Okay, all right, so I should have, yeah, I should mark the dot there to show that is the positive 20 dB per decade, and then I can start drawing the line with that slope. Okay, yeah, I'm heading towards that dot, okay, because that's the slope that I want. Okay, but I don't want to extend my line until there. Why? Because I need it to make it until PC point only. Where is your PC point? My PC point is 129. Yeah. Sorry, 120. Okay. 120.49 is my PC. So it means that, can you see that? What happened? Yeah, it stopped until there before it goes straight once more time. Okay, do this now. Okay, plot for me that GC line. Make sure you label. Okay. Any question about the GC plot? How to draw this? I hope that you understand. Yeah, but if you need help, okay. I have to switch off my video, okay? My battery is running out. Okay, so is it okay? Are you doing it? Yeah, 10. Okay, step number 10. We have this one, yeah, omega bandwidth desired. Okay, we put a name there, yeah. Yeah. All right, so that is 46. I follow the Fitri, okay? 46.594 radian per second. Okay. Okay, you're looking for omega bandwidth design from the graph, yeah, from GCG. Okay, but you are doing the graph yet, yeah? So not yet there, okay? For this one, I think we will continue next week because you're going to draw, yeah? But up to now, I need you to draw for the GC, okay? GC, GC, yeah? Make sure you draw that, okay? Not next week. This week on your class is on Thursday, right? Okay, we should finish late this week, Thursday next class. Okay, now is there any problem plotting the GC? Can you tell me what's your how's your drawing? I mean, are you doing okay?
Okay, madam.
Okay, right.
Okay.
Now, okay, so this is the thing, yeah. Okay, so how to draw this red color, red line? Okay, you can some, of course. Yes, some can. Okay, but it's very small space there, right? Okay, I want to show you, yeah, something here, okay, so that you can try at home and plot this red color, yeah. Okay, ready? No. Yeah, maybe you need 2 minutes more, okay, before I start, okay. 2 minutes, okay, finish your GC. Yeah, GC is where with this one, okay. Okay, let's continue. Okay, so this is your GCG, yeah, GCG equation as what I've told you just now. Yeah, you combine the GC with the G. Okay, looking at the equation. Yeah. Okay, look here. Okay, you know how to normalize the equation. Okay, you know you're good now. Yeah, with the sketching. All right. You use J omega, normalize it. Yeah. Okay. Now, during your normalization, you can see that, okay, when you take out this one, the value, let's see there, and the PC, okay, this is J omega. Okay, just imagine, yeah. Okay, take out, when you take out, okay, you actually cancel out the KC because KC itself is PC over ZC becomes 1. Yeah, the constant here becomes 1. Right, so that is the reason why it is a unity gain, yeah, as written in the number 9. Yes, step number 9, reset the gain with the lead competitors gain, yeah, because you don't want any additional gain that could disturb the starting point. All right, so it means that you can still use the same starting point when you first use the K equals to 1440. Okay, all right, so it means that your line is still the same. Yes, it's still the same until the alien comes, yeah, which is the ZC. Okay, until that point of frequency, then you have your graph shifted up. Okay, so how to plot this? Yeah, you can use your table. Yeah, to understand this. Yeah, okay. Look here. This is not actually table. This is the line graph. Okay, this is the another method that you can use to get the total slopes. Okay, all right. I don't think that it's difficult for you to understand this. Okay, let me explain a bit. Yeah, okay. As usual, you have your all the factors line up. Yeah, so here s plus 36 inverse, s plus 100 inverse. Okay, and the additional zc no inverse, and the pc inverse. Okay, because you have that 1 2 3 4 5, yeah, all lined up. Okay, all right, next, for the integral factor, you have minus 20 dB per decade slope all the way, start from the beginning. Yeah, okay, so the red axis here, okay, this is where I put the corner frequencies, or the the constants, yeah, from the factors. Okay, now, yeah, you have ZC then PC added together, because you're talking about GCG now. You want to draw the GCG, yeah. Okay, so you have ZC and PC added. Okay, so your ZC, my ZC is lesser than 36, so I put it first, and then my PC is greater than 100. I put it later after 100. Yeah. Okay. ZC is this is what? This is a first order numerator. Yeah, because it is up there. Okay, based on the board plot slide. Yeah. Uh, right from the beginning when we started chapter 2. Okay. For the first order numerator, it should give you plus 20. Okay, there you are. Starting from ZC, I have plus 20. Guys, are you there? Is it okay? Okay, I finish first, then you ask question, okay? Yeah? Okay, S plus 36, yeah, or the J omega over 36 plus 1 inverse, yeah? That factor is a first order denominator. So you have, as usual, minus 20 all the way, right after 36. Okay, 100, after 100, where is my 100? Here you are, my 100 there. Okay, after 100 you have minus 20, and then your PC is after 100. So yeah, after PC, yeah, the value of PC, then you have minus 20 dB per decade. Okay, sum them all downwards. You can use your slope table. Okay, no problem. Okay, this is just another representation of how to calculate the total slope across the frequency. Okay, okay, so here 0.1 to ZC. 0.1 to ZC, I sum the value, yeah, minus 20. ZC to 36, I have 0. Why? Because has the minus 20 has been cancelled by the slopes from the ZC. Okay, so ZC to 36 is 0. 36 to 100 is minus 20, and so on and so forth. Okay, now looking at the slope, yeah, I plot. Okay, now look here, from this one is ZC. Look at my cursor, ZC here. Okay, now the line starts there. Okay, because the additional effect, yeah, given by the lid, yeah, starts from that, yeah, because of the GC looks like that. Okay, before nothing. So means that the line would be the same, line for GCG until there, until there. Okay, until there. From ZC, this is ZC to 36, 36, 36. Okay, ZC to 36, it should have 0. Okay, 0 slope means straight line. You understand what I mean? Yeah. Okay, so from 36 to 100, I should have negative 20 back one more time. Negative 20 again. Yeah, so plot minus 20 dB until 100. Wait, where is my 100? Is here, 100. Okay, until 100. I sketch. Okay, not to worry too much about the slope. Yeah, you should understand now that you can just take the slope from the other lines that you have already drawn. Yeah, so here is already minus 20 dB per slope, per decade. Yeah, 20 dB per decade. So you can make that parallel, yeah, with that line because you need minus 20. Okay, next. Next, you know that this original line is minus 40. Minus 40 you should have for the GCG after 100 to PC. Yeah, so from 100 to PC, where is my 100? 100 to PC. Here, very short. Yeah, not easy to look at. Yeah, so minus 40. That's why you can use whatever that you have plotted just now. Okay, the slope is very useful to use. Okay, so this is minus 40. Okay, make that parallel with this because you just need it from here to here. Yeah, okay. Next, after PC, which is 120 uh, from me, yeah, 120.49 just now, yeah, my PC. Okay, for my PC, there is my PC. That's why you need to label, yeah, it's for easy for you, yeah. Make a dotted line all the way up here. Okay, from there, you just follow your minus 60, minus 60 dB per decade. Okay, that's how you can draw the red line. Not difficult, yeah. Okay, after you understand back the concept of drawing the boat using slopes, then you can see that, oh, this is doable. Okay, any question? Can you try this out? Okay, I will continue step number 10 next week. Again next week, not next week, next class. Yeah, Thursday. Okay, we will finish step number 10. Okay, on Thursday. Okay, because now it's already 1:50, not enough time. Okay, I need you to draw first. Draw, and those who have finished, tried drawing this GCG magnitude curve, yeah, you can share with me your answer. All right, you can share with me. Um, all right. I think it's good to have uh, it's good to have GC, right? So that you can submit there. Yeah, okay. I will open up an assignment, yeah, for this exercise 11.3, and please, yeah, try and draw the GCG. Submit your answer there, your graph, yeah, graph there, so that I can check for you. Okay, and yeah, of course, on Thursday I will open up your graph, and we'll discuss from there. Yeah, we'll discuss from there about your GCG, whether you need to correct it or is okay or not. Yeah, and then we finish, yeah, it with checking the omega bandwidth from the design. Okay, step 10. Can you try? Okay, try this GCG, okay? Guys, anything?
Sure, madam.
Christian, can you try draw this? Daniel, can you try? Yeah, for Thursday, okay? Okay, so for 10, okay, written already there. Okay, we will finish 10, yeah, on Thursday. Okay, any question? Okay, you don't have to use my line method. Yeah, you can use your table of slopes. Okay, as usual, you draw one table. Okay, now you have to consider the ZCPC, and what I want is the total slopes there. Yeah, according to the all the corner frequencies. Okay, corner frequencies, the constant. Yeah, of your factors. Okay. Okay, try and draw GCG. Yeah, I will open the GC for you to submit. Okay, I will inform you. Yeah, I think you will get the notification, right? Yeah, for chapter 2. Okay, the code for the attendance today is 4597. Please sign in. All right, thank you for joining the class. 24 of you. Okay, all right. Yeah, okay, please try. Yeah, I know that you can. Yeah, you go back to the table slope. Table of slopes. All right, guys, thank you very much. See you on Thursday.
Thank you.